So when I look at the first one asks the question, how far did Al travel in 3 hours? Does anybody think they got the answer to this one? So we can see, if I want to know, here's the time when it was 0 hours. 1, 2, 3. So if I go over to, you're correct. It's not represent the path on which Al is traveling. It's just the distance traveled versus time. I don't know exactly where he was traveling. He could have went somewhere and came back. He could have turned a bunch of different times. It's hard to say for sure. We just know over 3 hours he traveled 54 miles. Okay, what about C part? What was Al's average speed in miles per hour for the time interval? Okay, so look at this. Look at this over here. What is this telling me?
0 to 3.
Yeah, when T, right, this kind of looks like when we write our domain. You guys remember writing domain before? T is between 0 and 3. So we're looking at the graph where time was between 0 and 3. What was his average speed during this time?
36 miles per hour.
Okay, and how did you come up with 36 miles per hour?
Well, I did 18 plus 36 plus 54 and divided it by 3.
Okay, but we're not looking at, okay, let me just say no. Okay, that's not the correct math to find it. Let's think about it like this. If I was starting here when time is 0 and I'm ending here when time is 3, what's the distance that was traveled between 0 and 3? 54 miles is all that was traveled. And how long did it take her or him to travel 54 miles? How long did it take them to travel 54 miles? 3 hours. So they traveled 54 miles in 3 hours. So you would do the division, 54 divided by 3, which is 18 miles per hour.
You could have did that from the first point, though. That's how I did it. Yeah. I looked at it from each one is increasing by 18.
No. That's not the speed. It's not showing you the speed. It's showing you the distance traveled over an amount of time.
No, like each hour.
In the first hour, how much distance was traveled?
18.
In the second hour, how much distance was traveled? No. In the second hour, we'd just be looking between 1 hour and 2 hours. Where did he start at an hour in? He already was 18 miles ahead. And so he only went an additional 18 miles to get to a total of 36. So after 2 hours, he went 36 miles divided by 2 hours, which would still be 18 miles per hour. Because we can tell by the line, because the line is a steady line, that his speed is constant the entire time. Right? Speed doesn't change. And we're actually going to get to that in just a second for E part. It's a bicycle. Cyclist.
Some people run faster than that.
Yeah. For a short amount of time. Right? Not for 2 hours. You can't sustain 18. But yeah, like football players, during a football play, they can run 21, 22, the fast guys. 22 miles per hour. But you're not going to maintain 18 miles an hour for 3 hours. It's just not. Now, they can maintain about 12 miles an hour, maybe 14. What is Al's average speed in miles per hour for the interval between 1 and 2? So we kind of already talked about this. Between time 1 to 2, how much distance was traveled between 1 hour and 2 hours? He started at 18 miles in, and he went up to 36 total miles. So how could I find the distance traveled between 18 and 36? You could just subtract them. 36 minus 18 means that he traveled 18 miles when I do that subtraction. And then how many hours did that take? Well, we would subtract that too. Right? 2 hours and 1 hour gives me a total of 1 hour. So again, that same rate is 18 miles per hour. So is Al's average speed increasing, decreasing, or remaining constant? It's constant, and we can see that because it's a line. Are there any questions on this first one? This is about as easy as we can make it.
Well, now that I know, because I missed every single question,
It's not even easy.
I know.
Okay, I want you to try the back page, same deal. I'm going to give you a little bit more time to do it. Let's go 5 minutes, and then we'll talk about it. Okay, so if I look here, A says, what is Al's average speed for the interval 0 to 5? So we're starting at time being 0, and we're ending at time being 5. So what was the distance traveled between 0 and 5? It was going 60 miles. And how long did it take it to go 60 miles? 5 hours. So what is 60 miles divided by 5 hours? 12 miles per hour. Are there any questions there about finding that speed? Now when you look, we can tell by looking at the graph. Was Al going 12 miles per hour the entire time? No. He may not have ever been going 12 miles per hour. But over that entire time, his average speed was 12 miles per hour. Okay? B, what was Al's average speed for the interval between 0 and 1? So now we're only focusing between time being 0 and time being 1. So he started with a distance of 0. He ended with a distance of 18, which means the distance traveled was 18 miles. And the time it took Al to do that was 1 hour. So that would be 18 miles in 1 hour, or 18 miles per hour.
That's pretty slow. He ain't on the bike. This guy.
Sure he is. He's on a bike.
Is he?
It's still Al. Yeah. Look at C. What is Al's average speed for the time interval between 1 and 2? Okay, so let's look. Where are we looking between 1 and 2? So let's draw where that's at on the graph. So we're looking between 1 and 2. So what was his starting distance? He was already 18 miles in, and he ended up stopping after the 2 hours at 33 miles in. So what distance did he travel if he started at 18 and he ended at 33?
15.
He traveled 15 miles. And so the way we would find that, we would do 33 minus 18, which was 15 miles. And then we need to divide this by the number of hours.
1.
In this case, going from hour 1 to 2 was a 1 hour time difference, which means Al was traveling 15 miles per hour at that point. We look at D. D is talking about the interval between 2 and 4 hours. So this is the part we're focusing on, between 2 and 4. So first, we know speed is distance divided by time. So how much distance did Al cover between 2 and 4? Well, he started at a distance of 33. He ended at a distance of 42. So how much distance did he cover?
6.
So he started at 33. He ended at 42. So to find the distance, we could subtract 42 minus 33. Which is 9 miles. And how long did it take him to go 9 miles? 2 hours. Right? We could get that by doing 4 minus 2 for the hours. So this would be 9 over 2 or 4.5 miles per hour, right? Not 4.5 hours. 4.5 miles per hour.
Why did I write 6? Why did I do 6?
Okay, let's look at E. What does E tell me? The average speed for the time interval between 4 and 5. So now we're looking here between 4 and 5. What was the finishing distance? Finished at 60 minus, what was the starting distance? 42. Which means we traveled 18 miles in how much time? Well, that would be 5 minus 4, which is 1 hour. So 18 miles in 1 hour, or 18 miles per hour. According to the graph, when was Al cycling the fastest?
0, 3, 1, and 4, 3, 5.
Okay, so between 0 and 1, we found he was going 18 miles per hour. And between 4 and 5, we found he was going 18 miles per hour. So we're going to say when time was 0 to 1 and 4 to 5. And now what does that look like on the graph? Where he was going the fastest, what does that look like? Like, how could we know he was going the fastest there just by looking at the graph?
More of a steeper slope.
Steeper line. You see how here, between 0 and 1, that line is very steep. Y'all know what I'm talking about with steep? Like the pitch of a house on a roof, right? It's called steep. It can be a steep roof, or it could be a very flatter roof, or like the main building over there. You know how flat that roof is over there? So, because this one is steeper, that means the rate of speed, or the rate of distance versus time, is greater. What would it look like if he was going faster between 0 and 1? It would be even steeper, right? Or if I want to go even faster, I need to go even steeper. The steeper the line, the faster he's going. That's what it means by explaining in terms of the graph.
So I could do it right saying that the graph was strong.
That's where the graph was the steepest. Was between 0 and 1 and 4 and 5. Where is the graph where was he going the slowest?
2 through 4.
Between hours 2 and 4. And what does that look like on the graph?
More flat.
It's a more flat line, right? Not as steep, more flat.
Am I noisy or something? No, I just feel annoyed. I think I made it.
What we just got done talking about with the steepness of a line, we have a vocabulary word that we use for that. It's called slope. So, for vocabulary, slope is the steepness of a line. Slope is the steepness of a line. We have a bunch of different ways we talk about slope. Okay, sometimes we call slope the rise over the run. We could call it the change in Y over the change in X. Sometimes it's written as delta Y over delta X. But these are all different ways to talk about slope. What do y'all think they mean by rise over run?
Rises and then it runs.
If you pick 2 points on your graph, we can talk about how much does it rise, how much do I run? Right? Rise over run. In algebra, anytime we're talking about slope, we will use a specific variable. We use the variable m. If you ever see the variable m, we're more than likely talking about slope. And now the last thing we're going to do is we have a formula. What were we just doing in order to find the slope?
Is it y equals mx? We're about to use that.
Y equals mx plus b.
Okay, that is called slope-intercept form, what y'all are talking about. But that's not the formula for slope. But slope-intercept form gives you the slope.
The y2 minus y1 over x2 minus x1.
And you see how we just did it without having a formula, right? We subtracted our ending distance from our starting distance. And then we divided by our ending time minus our starting time. You were using the slope formula without actually plugging into a formula. You're just doing it using common sense. But that's what we're going to do, is use that slope formula. M equals y2 minus y1 over x2 minus x1. When we do this, we want x1, y1 to be our starting point. And we want x2, y2 to be the end point. Now, all this that we're doing is because we are graphing a function. What's a function? A special relation where every input has exactly one output. Look at this graph. Does every x value have exactly one y value? Yes, it does. Every x has one y. It passes the vertical line test. Anywhere I draw a vertical line, it only touches the graph once. So we're talking about a special kind of function, one that graphs as a line. It's called a linear function. And that's what we're going to be working on. So this would be continuous, right? Again, talking about what we've been talking about before. Discrete means points. Continuous means we can connect it with a line. Okay, so on the back, we're doing the same thing. We want to find the rate of change, which is just the slope. Average rate of change, the slope of the line. The deal here is, this graph is giving you 2 lines. So I need to determine, what's my x value in this chart? Where's my x value shown? Because we want time to be x, to be our independent variable. So the years, these are my x values. Okay, what's my y value? The population. So really, if you want to think about it, this is its own chart of an x value and a y value. And then you also have the year and the bottom one as a second chart of x values and y values. So you're graphing 2 graphs at one time. So they're going to ask you for the slope of each. So like on the left side, it's only asking you about city A, which means we would be looking at the year and city A points here. What's on the right is only talking about city B. So we'll be using the year and population for city B. Okay, so I'm going to give you a chance to try to do it. Find the slope, given points. how are you going to have to find the slope? You're going to have to use the formula because you don't have a graph. Right? You're going to do exactly what we were doing before.
Actually, yeah.
So we said the years would be the X values and the population would be the Y values. So how much did my population change between 1990 and 2000? So what was my ending population in 2000? 72,000. And what did I begin with in 1990? So how much did my population grow by? 30,000 people, right? We can find that by subtracting. And how long did it take the population to grow by 30,000? Well, we could take our end year, which was 2000, and subtract our beginning year, which was 1990. So this would be 30,000 people divided by 10 years, or 3,000 people per year. Can you guys do this now, or do I need to do another one? All right, let's look at City B between 1990 and 2000. So what was my, again, we're doing the change in Y over change in X. So let me write it this way. What's the first ordered pair for City B? Well, in 1990, the population was 75,000. And then the second ordered pair is in 2000, the population was 60,000. So, again, the formula. This is my X1, my Y1. This will be my X2 and my Y2. Sorry, that didn't show up good for you guys. Let me change the color. Okay, this is my X1, Y1, X2, Y2. That's crazy. The green shows up better. The green shows up worse on my iPad, but better. It's crazy. Okay. So now plug into the formula. I'm going to go Y2. That's my ending population. Minus Y1, my beginning population. Divided by X2, my ending year. Minus X1, my beginning year. And I can put all this directly in my calculator, right? 60,000 minus 75,000 on top of your fraction. And then 2,000 minus 1990 on the bottom of your fraction. If you need help putting that in, let me know.